Okay, so last time we defined what a rational number is. So last time we defined a rational number to be one that we can write as a quotient of two integers. And shockingly, there are numbers that are not rational, and those are called irrational numbers. And that's quite, I mean, to me, that was quite a shock that such numbers should exist. So a number is not rational if it cannot be written as a quotient of two integers. And such numbers are called irrational numbers. And I'm pretty sure it was with you guys that we proved that square root of 2 is irrational, that there cannot be two integers, so that if you divide one by the other, you get a number that squares to 2. It's just not possible. And so our number system would look like this. It is a set of all natural numbers closed only under multiplication and addition. If we want to fix subtraction, we threw in 0 and the negative integers and got the integers. And then the integers, the set of all integers, is now closed under addition, subtraction, and multiplication, but not yet under division. And when that was fixed, we got the set of all rational numbers. You can think of them as fractions or fractions and integers. Every integer is a rational number because, say, the integer 5, it can be written as 5 over 1. So subset. The set of all integers is a subset of the set of all rational numbers. And then there are the irrational numbers. And together, those two sets make up the real numbers. And I wanted to show you with the, I'm not sure if I managed it, that there is actually not only these irrational numbers like square root of 2 or pi, not only that they exist, there is actually more of them than the rational ones. Let's see, here is 2/3, here is -5, 0, 1, 2, 99, and so on. So that's our number system. And the real numbers, they live on the number line. So the number line establishes a pretty fundamental connection between algebra between algebra and algebraic things and geometry, visual things. Even the word number line, right? Number is an algebraic concept, line is a geometric. And so for every point on the line, there exists exactly one real number, and vice versa. For every real number, there is exactly one point on the number line. So there is a one-to-one correspondence between the set of all real numbers and points on a line. So there is a one-to-one correspondence between points on a line and a real number. And I'm sorry, points on the line and real numbers. And a one-to-one correspondence means you can pair them up. So for every number, there's a point. For every point, there is a number. Okay, so that's our number system. And last time we talked about things like, is 1.2 rational? So is this number rational? And if yes, why not? So it's all about the definition. So a number is rational if you can write it as a quotient of two integers. Well, one very generic way to do this is to say, well, I want a quotient. Okay. Now we have a quotient, but now we want a quotient of integers. And if you look at this quotient as a fraction, we are allowed to multiply upstairs and downstairs by the same number, and we will not change the value. And 10 would fix the number on the top, right? 1.2 times 10 is 12. And so 12 over 10, that is that 1.2. So 12 is an integer, 10 is an integer, therefore 1.2 is a rational number. If a number is rational, it's quite easy to prove that it's rational. We just have to produce two integers that do the job. If we have to prove that a number is irrational, that's a much harder task because we have to defeat every possible attempt. We have to say, no, that's not going to work. No, that attempt is not going to work. So imagine that we have to deal with infinitely many fractions where we're considering every integer on the top and every non-zero integer on the bottom. So that's quite a lot of them to consider with our finite life and finite time. But if you look at this technique, basically this tells us that every terminating decimal represents a rational number. It could be long. A terminating decimal has a last digit, so it could be long. This has a last digit. So we're going to grow a 1 and then multiply upstairs and downstairs by a suitable 10 power. So we grow a 1. We wanted a fraction of integers. Now we have a fraction. Now for a fraction of integers, we need to multiply this by a 10 power. And what 10 power is that? So move the decimal till the end. How many times do we move it? 1, 2, 3, 4, 5, 6, 7. So we're going to have to multiply. Now, either you write 1 and then 7 zeros or 10 to the 7th power. Luckily, that's the same thing. 10 to the 6 is a million. So we're multiplying upstairs and downstairs by 10 million. And then we get 102, 752 divided by 10 million. And so you will see the language that I'm going to ask you to prove that a number is rational by rewriting it as a quotient of two integers. And the nice thing about that is you don't have to produce the best one. You do not have to reduce this thing to lowest terms. As a matter of fact, 6 over 5, it's harder to see that it's 1.2 than 12 over 10. So whenever I ask you to convert a decimal to a quotient of integers, you never have to simplify it because the point is that exists. You don't have to find the best one. So I hope we're convinced that terminating decimals always represent rational numbers. Backwards, it's not the case because let's look at 1 over 3. And this time I want to look at long division. Kind of a claustrophobic experience. So 3 goes into 1, now it doesn't. So we write down the 0 and then we cross the decimal. And so now we can multiply back. 3 times 0 is 0, subtract. We just have that 1. And then we bring down a 0. And now 10 divided by 3, the answer is 3. Because 3 times 3 is 9. Subtract. We get a 1. Bring down the next 0. 10 divided by 3 is 3. Because 3 times 3 is 9. See, it's a little bit, we're stuck in this loop forever. So a terminating decimal means that we are dealing with a rational number, but backwards it's not true. Not every rational number, when we write it as a decimal, terminates, and 1/3 is a great example. 1/3 is 0.3333. Lots of threes there. There is notation for that. But this is already kind of a gentle push from decimals towards fractions. You cannot really precisely compute with dot, 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 and infinitely many decimals. This is much simpler. But there is notation for that 0.3, and then the repeating part gets a bar. Let's see another one. How about, I don't know, 5/27? You see, this one is a repeating decimal, and we can check that by a long division, but the repeating block is longer, 0.185, So you have to be careful to identify when you see this bar notation, what on earth is being communicated to us, because 0.185 with the bar like this means that only 5 repeats. That's the repeating block. So that's 0.1855555. On the other hand, 0.85 with a bar like this has a 2 digits long repeating block. This is 0.185858585. And finally, 0.185 is 0.185. Okay. So there are several questions here, but we're actually looking at decimal presentation. So we know that if the decimal presentation is terminating, then we're dealing with a rational number. And we already know that backwards, that's not true. Rational numbers can be this infinite repeating thing. So we could say, okay, what about the repeating decimal? Is it always rational? Or, you know, some of the repeating decimals might be things like 1/3, and other ones might be irrational numbers. So what's the deal with repeating decimals? So do repeating decimals, I'm sorry, before I say repeating, so the actual term is do all non-terminating repeating decimals. So do all non-terminating repeating decimals represent rational numbers. So I think this is clear, but the terminating decimal has a last digit. A non-terminating decimal means that the digits go on forever. And that can be either repeating or not repeating. So we're going to first look at this repeating decimals. Well, we know that this particular one is a rational number because we started with an integer divided by an integer. But what about backwards? What about something like, well, we might recognize 0.33333, but what about 0.77777? Is this a rational number or not? So I'm going to show you how to prove that it is in fact rational. That's kind of a cute little application of simple equations. So the first thing that we're going to do is we're going to drop the bar notation and we're going to write this number 0.777. And we're going to call this strange number X. Now, visually you see 5 sevens, but it really is trying to indicate infinitely many, right? So the dot, dot, dot means there are infinitely many sevens. And so because of that, there is some strange property. Infinity has some strange properties. So what we're going to do is going to be kind of strange. We're going to use the number's own badness against itself. But first, we're going to have to modify the number a little bit. So we're going to do two things. First of all, we're going to multiply both sides of this weird equation by 10. Second, I'm going to write the new equation above the old one. So we're going to multiply both sides of this weird equation by 10. Well, 10 times x is going to be 10x. What happens to a decimal when we multiply it by 10? Well, we just promote the decimal, right? It's going to become 7.7777. And so this is crazy unless you have the dot, 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 because if you don't have the dot, 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 then suddenly magically you went from 5 times this digit 6 times. And that's not possible. But the dot, dot, dot is telling you, wait a minute, no, we're talking about infinitely many. So there is a 7 above this one, even though we kind of shifted this. And so now comes the fun. This is the part that I call chop chop, because we're going to cut off the infinite tail of this number by a slick subtraction. So we're going to subtract the second line from the first line. 10x minus 1x, well, that's just 9x, right? And now we're using the number's badness against itself. When we subtract 7.7777, I mean 0.777 from 7.777, we have perfect alignment. You see, that's why I wrote the decimals under each other. And we just get 7. And now look at this cute little equation. Solve for x. X is 7/9. Now we can check via long division or with the calculator. But when we check with the calculator, something strange is going to appear. 7 divided by 9. You see this 8 here? This is rounding. So 77 was rounded up to 80. And that is not an issue with 1/3 because 33 was rounded down to 30. But whenever, so I don't want you to freak out about the last digit. When that last digit is 5 or above, we get rounding. But it's correct. So this is how we do this one. Any questions so far? All right, so let's do these three. So, well, no, we're not gonna do this. Well, we can do the third one, even though you remember where that third one came from. So let's do 0.18555555. By the way, usually 3 is enough, both the dots and the 5s. I have a bit of an OCD, so I just want to keep going. All right, so we're going to multiply both sides of this strange equation by 10, and we're going to write a new equation above the previous one. And because the next step is a subtraction, we must align by the decimal point. So when we multiply by 10, we get 1.85555, 1.85555. And now when we subtract, we don't quite get an integer, but as long as the infinite tail is gone, we should be celebrating. So we have 9x again, and 5 minus 5, 5 minus 5 is all good. And then we have here, I guess you can ask the calculator this one. What is 1.85 minus 0.18? Because these simplify from 0. So we can punch this in. I'm going to attempt to do this on paper. I need the practice, as it turns out. So 15 minus 8 is 7. 8 minus 2 is 6. So I'm getting 1.67. But again, if you can just cover the part that's identical, that is the subtraction we need. So we have 1.85 minus 0.18. Oh, I got it right. Okay. So as long as the infinite tail is gone, we're in good shape. But if we divide both sides by 9, we don't get an integer over an integer because this is not an integer. But as long as it terminates, we're fine. So all we got to do is, there is an easy fix for this, right? Multiply both sides by 100. By 100 because we need 2 decimals to fix this terminating decimal to become an integer. So here we multiply by 10. Now we're going to multiply by 100 because this number times 100 is now an integer. And 9x times 100 is 900x. And now if we solve for x, we get 167 divided by 900. Looks like fun. Again, with me, you never have to worry about simplifying. 100, so 167 divided by 900. You see the 6 at the end? That's rounding. 55 was rounded up to 60. So our answer is correct. Any questions? Okay, so our next number is 0.1858585. Okay. And now don't think about it from beginning till end. There is no end. Think about it digit by digit. What happens to a decimal when we multiply it by 10? Well, this one was the 1/10th. It will be promoted to be the ones, right? The decimal moves. But this one that was the 100th place will be promoted to the 10th. So every decimal, no matter what place value it represents, will be promoted to 10 times as much. Well, because we multiply by 10, right? So here is the problem. If we multiply this number by 10, it's not going to work because then this 5 will be promoted here. And so let's see. So we get 1.85858, 1.8585. You see what the issue is? That doesn't work because either this infinite subtraction is not even defined, or if it is defined, we're just changing the infinite tail, but we're not eliminating it, right? The only way this technique works is when we have an 8 over an 8 and a 5 over a 5, which means that when you grab this number 8 here, you need to promote it by 2 decimals, which means we need to multiply by 100 instead of a 10. There is a perfect match. Basically, you just have to look at how many digits long is the repeating block. That's how many zeros you need after the 1. So here, the repeating block is 2 digits long. So we're going to multiply both sides by 100. And if we do that, the beginning is always weird. But if you just think about it from place value to place value, then it is a little bit more sensible that this will always work. So we're going to get 18.585858. And that sounds bad because we had 858585. But let's see, 18.5858, 18.585. Look, it works. And then make sure that you align them in such a way that you can subtract it correctly with or without the calculator. But basically, this slick multiplication by a 10 power only works if you have identical digits above each other, so the subtraction will chop off that infinite tail. So if we subtract x from 100x, we're going to have 99 many. And here, gone, gone, gone. We're going to have a little bit of a decimal, right? Gone, 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 gone. This is it. Well, that seems a pretty easy one, right? 18.5 minus 0.5. That's just 18.4. That seems almost too easy to be true. So we have 18.4. And again, we didn't get an integer, but as long as we got the terminating decimal, it's an easy fix. We just fix this by multiplying both sides by another suitable 10 power. And they're completely independent. Here it was a 10 first and 100. In this one, first 100 and now 10. But that's completely unpredictable. In the first case, how many digits long is the repeating block? In the second case, well, what 10 power will fix this terminating decimal? So if we multiply both sides by 10, we get 184 here and 990x there. And when we solve for x, we get 184 divided by 990. And as I said, you will never have to simplify this. But you should check with the calculator. You will have no excuse for turning in an incorrect answer because you can check with the. That 6 is 58 is being rounded up to 60. So our answer is indeed correct. Okay. So the last one was 0.185, The 0 is not repeating. And now, if we want to multiply by a 10 power, so that after the multiplication in the infinite tail, a 5 is above a 5, 8 is below an 8, a 1 is below a 1, then we have to promote this decimal to be 1, 2, 3. We have to promote it by 10 decimal places. That means we have to multiply both sides by 1,000. So when we do that, we know that the next step is a subtraction. So we align it decimal by decimal. So when we multiply this number by 1,000, we just get 185.185.185. So 185.185.185. And then after subtraction, we get 185 here. So no need for the second fix, and 999x here. And so x is 185 divided by 999. So our number is correct. Any questions? Okay, so let me write down the so the first 10 power. We have to ask, how many digits long is the repeating block? How many digits is the repeating block? That's how many zeros we have to put after the 1, which is the same thing, is that should be the exponent on 10. So if 4, then 10 to the 4 equals a 1, and then 40 after is what we need to use. If 7, we're going to have to use 10 to the 7th power. Now the second 10 power, which you may or may not need, is to fix the terminating decimal that we get. Right? After we eliminated the infinite tail, we might be left with terminating decimals. Then you just ask, okay, how many decimals what 10 power do I need to multiply to fix that terminating decimal to become an integer? And that's basically how many decimal places do I need to move the decimal point to the right? 2 here, 1 there. That's how many zeros we need to put. So the second 10 power is what 10 power will fix the terminating integer. The terminating decimal. What 10 power will fix the terminating decimal? All right. Would you like to see one more example? Or you guys kind of got it? You're not going to have to know this for this Thursday, but starting next week, Thursday, you're going to have to know it. Yes, go ahead.
Oh, yeah, I was going to say I'd like to see one more example.
Okay. All right, let me make up something. Okay. All right. I think we can fit the whole thing. So the number is 5. 6193193 6193193 Okay. Usually the first step, you're going to have to translate this number from this form, which I already did accidentally, right? And make sure, people get this right, but often people lose points because they don't solve the problem that was asked, especially with a 1. So you can always ask me what's exactly under this bar. Right now, the repeating block is 3 digits long, which is why we're going to have to multiply both sides of this strange equation by 1,000. We have to use this 3 has to be promoted to be above this 3. Or if over the 9 it doesn't help, over the 1 it doesn't help. So we're going to multiply both sides of this strange equation by 1,000. Then we get 1,000x on the right hand side, and on the left hand side, well, 1, 2, 3. So we're going to have 5,619.319319319. And it's strange because it's no longer 193, it's 319319331. So 5, 1, 2, 3. So 5,619.319319. You really want to align them by the decimal place and don't fake it. You actually want to see that is actually helping you. Okay, so now the infinite tail is going to be cut off if we do the subtraction. So gone, gone, gone. So if you want to enter it in the calculator, this is what we need to enter, right? 3,619.3 minus 5.6. So again, I'm going to attempt to do it in my head, I mean with paper, because you don't use it, you lose it. 13 minus 7, 9. On the other hand, don't trust me with numbers. So we have 3613.7. Oh, sorry. 3619.3 minus 5.6. Good. And the other side is what we get when we subtract x, 1x from 1000x, and that's 999x.
Why is it 3619 and not 5619?
Well, they all can be interpreted in every kind of because of the shifting, I think, that this so it's 193193, right? But this one and this 9 and this 3 became sort of part of what we subtract. And the first thing that started to become the same is 193. It's just this part was used up, sort of. But actually, to be completely honest with you, we could rewrite even this one as 5.61931931931, right? So with this bar notation, the decimal presentation is not exactly unique. As long as you get the same thing, if you read it out, right? 5.6193193193193, we get the same thing. So if we wanted to, we can rewrite this upper number as 3619.3193193. So we can, you see this one was partially used up in the subtraction. And that's why it starts. But it's kind of, as long as you get the same thing, when you read it out, you're fine. So there are several different ways to express this. Here is another example. 0.2525 is 0.25252525. Well, we can just say, well, you don't have to repeat the 4 digits. See, there are more than one ways to write these things. So pretty much that's what's going on. But at first it sounds strange, and so I don't want you to see this first in a quiz or an exam. So does that answer your question? All right.
Yeah.
Good. So we subtracted. Now we fix the terminating decimal because, and I will try to always include in the instruction that prove that the number is rational by rewriting it as a quotient of 2 integers. So the goal is to prove that this crazy decimal is a rational number, which means integer over integer. This is not an integer, but there is an easy fix. And this time we just need one decimal. So we can use 10. So we have 36137 equals 999 and a 0, x. So when we solve for x, we're going to have 36,137 divided by 9,990. So 36,137 divided by 999. Oh, 36. Oops, something went wrong there. You see, that didn't check out. We lost. So something is wrong. We didn't get it right. So let me just check my own subtraction first, because probably that's what I messed up. Did I mention you lose it if you don't use it? 3619.3 minus 5.6. 3613.7, 3613.7. But maybe I punched in the incorrect thing. So 36137 divided by 9990. Oh. Oh, wait, that first thing should be a 5, right? This
That's
3.
why that's what I was asking about earlier.
Oh, you were right. I was wrong. Sorry. So let's try with 50. 5, 6, 1. So you see, it's this checking is not really faking it. It's really saves you a lot of points in exams. Oh, good. So we got 5.6, 193, 193, 193. That is completely forgivable, but it's an important thing in algebra to be able to read your own handwriting. You know, that's not even within the jurisdiction of mathematics, but it's going to mess you up in algebra. For example, I can not use the variable t because it reads just like my plus sign, or z that reads just like my number 2. So you kind of have to figure yourself out and avoid those danger spots. All right. So this is what I'm going to refer to as a chop game. I have videos. I have one with 2 decimals, one with 3. Yeah, so I have 2 different videos. The problems will come with the videos. But I want to warn you that there are 2 different methods. And there is another method. And if you go to pretty much anyone else, you're going to see that other method. I don't care which one you use, as long as you understand it. But there is a reason. That other method might be more elegant, but this one will rhyme later on when we come back to it. We're doing exactly something that we will later do. So I have my evil reasons to present you this one. So either way, this chop game sort of serves as proof for the following fact. If we have a decimal that is not terminating, but it repeats, that too represents a rational number. So a non-terminating repeating decimal. So a non-terminating repeating decimal represents a rational number. And I might have told you this last time, but it was around the end of the class. Notice the language here, that a decimal is not the identity of a number, it's a representation, it's a presentation of it. So whenever you say, I got a decimal, well, I don't know what kind of a decimal is that. So we usually will say, I got a fraction, or I got a rational number. So a decimal is just a very convenient way of writing them, but you cannot really describe the number by just saying decimal. Now, if you say a terminating decimal, that's a rational number. And if we have a non-terminating, but at least repeating decimal, that too is a rational number. That's what the chop-chop game that I just showed you proves, sort of. So are we convinced of this fact? And the repeating block can be as long as you want. You can have a 37 digits long repeating block. You can start with the decimal and go to the, you can have a 200 digits long repeating block. You can have the digits repeated within a repeating block, like 1107, 1107, 1107 would be one example. So let's talk about square root of 2 and how we can write square root of 2. Well. Square root of 2, and we proved it, is an irrational number, right? And anytime you grab a real number that is positive, but not a perfect square, its square root is going to be an irrational number. So there is no middle ground. It's either square root of 2, yuck, or square root of 9, nice. There's no in between. Now, if we want to write square root of 2 is kind of a strange description. It's not telling you how big it is. It's just sort of like driving instructions towards the number. The definition is, this is the positive number that if we happen to square, we would get 2. Let me write this down. This is the positive number that when squared, the result is 2. Now, because it's irrational, by definition of rational, irrational numbers, we cannot write it as a ratio of 2 integers, right? Because that would make it rational. And we proved that this is not. We actually proved that we cannot find 2 integers so that their quotient would be square root of 2. So it cannot be written. Now we can write it as a fraction, for example, square root of 2 over 1. But as a fraction of 2 integers, that we cannot do. As a quotient of 2 integers. In other words, we cannot write it in, as a fraction. Well, we can write square root of 2 over 1, but that does not get around the issue that this is a strange way of describing this. How big is this number? So then let's try to write it as a decimal. Square root of 2 as a decimal. If we punch it in the calculator, we can just see the beginning. You can have a terminating decimal that's 200 digits long, or a repeating one that has a 200 digits long repeating block. We have no idea. We just see the beginning. I'll get it. Now let me ask you this. Is it possible that square root of 2 as a decimal is a terminating decimal? No, it can't, because if we can write the number as a terminating decimal, we agree that terminating decimals represent rational numbers, but square root of 2 isn't rational, and we actually proved that. So the decimal presentation of an irrational number cannot be terminating, because terminating decimals always represent rational numbers. So irrational numbers as decimals cannot terminate. So no, terminating decimals represent rational numbers. Well, and square root of 2 is irrational. A number being rational or irrational is a fundamental property of the number. You cannot change its nature without changing its value. So square root of 2 is irrational. Therefore, it cannot be written as a terminating decimal, because that would make it rational. So what does it mean? Well, if it cannot terminate, that means that the digits of square root of 2 will go on forever. Okay, that's not good news, because we have finite paper, finite, even graphite. Even if we use all the carbon in the whole wide world for writing down this, we would run out of carbon. We would die first. We would run out of time. But so this number as a decimal would go on forever. Can it at least repeat? No, because that too would make it rational, right? We just showed with the chop game that repeating decimals too represent rational numbers. So as a decimal, can it terminate? No. Can it repeat? No. Because repeating decimals represent rational numbers, and square root of 2 is not rational, because repeating decimals So then what is left for poor old square root of 2 as a decimal? What kind of a decimal presentation will square root of 2 have? What is left? It's pretty bad. It doesn't terminate and it doesn't repeat. You can have all kinds of patterns, but you cannot have a repeating block, because that would make it rational. So consequently, we have a square root of 2 as a decimal must be non-terminating, non-repeating. Square root of 2 as a decimal cannot terminate and cannot repeat. Which makes it pretty difficult to write it as a decimal, right? Now, let me show you an irrational number. You can have all kinds of patterns, just don't repeat. So for example, if you write 0.1, and then you put in a 0, and then you put 1 again, and then in order to avoid repetition of digits, you put in 2 zeros, and then a 1, and now 3 zeros, and a 1, and then 4 zeros, and a 1. And you go on in this pattern forever, you're creating an irrational number. Because as long, well, we didn't prove this, but it's true backwards too, that any number that as a decimal is that ugly, that is irrational. So all the rational numbers are terminate or repeat, and all the irrational numbers are disgusting. They are non-terminating, non-repeating, just terrible, terrible, terrible. So this is an irrational number. And so in algebra, you will very often see the expression exact value. And you're going to see it in instructions of problems. You're going to see things like present your answer as exact value. Now, exact value is the opposite of an approximation. Is there anyone here who was taught that 22/7 is pi? Let us accept for now that pi is irrational. It is irrational. So then 22/7, which is rational because 22 and 7 are both 22/7 looks like pi, but it cannot be pi if we believe that pi is irrational. We have a pi button. I want to know if it's less or bigger than pi. It's just a very good approximation. That's what it is, especially considering how small these numbers are. So I'm going to subtract pi. We got a small positive number, but look, it's like 1,000. It's a very precise approximation, but it's an approximation nonetheless. So this one here is this tilde means approximately equal. So an approximation for pi, approximation for pi. And if we believe that pi is irrational, it cannot be the exact value because that would make pi rational. Also, if you write, say, square root of 2 as 1.4, that cannot be square root of 2 because 1.4 squares to, it's too small, right? It doesn't quite, it's close, but no cigar. And also it's rational, right? So this is an approximation. 1.41, again, it's rational because 141/100 is that, but also we can square it. And this is how we can get approximation of a square number, of a square root just by squaring. For example, 1.4 squares to 1.96 and 1.5 squares to, that's not gonna work, 1.5 squares to, that's too big. So it's somewhere in between 1.4 and 1.5. So it's 1.40 something. And then we can continue and say 1.41 squares to too small, but pretty close. And 1.42 squares to too much. And so you can lock it in as many digits. You can have as precise of an approximation of square root of 2 as you want, but as a decimal, you cannot achieve the exact value, right? Because we just don't have what it takes to write an infinitely long non-repeating decimal. We just can't do that. So if someone says you have to use the exact value, this is our only option. This is our only option to write square root of 2 as an exact value. And the idea is that this is the exact value, 1.4, 1.41, 1.414. These are just approximations with different degree of accuracy. And so when you present exact value, just think about it this way. Your reader might need an approximation up to 10 digits or up to 1 digit. We don't know. So why don't we give them the exact value, and then the reader can punch it in the calculator and get the approximation that they need. If you make this decision for them and you present your answer as 1.4, we will no longer know where this is coming from. It's 14/10 for all we know, right? So if you give a decimal approximation, you don't only lose precision, you sort of lose information. Most of the time, you're going to be asked for the exact value of these numbers, which is why, and this is sort of the beginning of completing the square, and this thing is the beginning of Math 99, because now, until our language of algebra, written mathematics, was numbers and letters, and now it's going to be nice numbers, yucky numbers, and letters. And so we're going to have to revisit the whole algebraic language with these symbolic things in them. And that's a big part, a very important part of intermediate algebra. That's sort of going from rational to reals. And so we have to use this radical form whenever you see exact value. And when will you see exact value? Pretty much every time. Later on in your next course, you might need good approximations. But for now, this is algebra, and algebra is kind of a purist language. So this is our only option, to write an irrational number. Any questions so far?